Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, today we're going to be learning about angle-angle triangle similarity. And basically what it is when you're looking at shapes and you're trying to solve problems that involve angles, sometimes recognizing that two shapes, two triangles might be similar to each other can be very helpful for you deciding on how you're going to go about solving the problem. So let's get right into it. Remember, as we're going through these lessons, please do not hesitate to pause, back up, rewatch, whatever it takes for you to get all the information down and for you to hear exactly what I'm saying about the processes we go through to solve these problems. In chapter 6, you learned that you can create similar figures by using dilations. Today, you will investigate what happens to the angles in a figure when you enlarge or reduce the figure to create a similar figure. This is something we've already talked about what happens when you dilate a figure with a scale factor of 2 or 3, or with a scale factor that's less than 1, like 1/3 or 1/2. So we'll get into that a little bit more. The very first problem is actually going to revisit that basic concept. So what you need to do, hopefully you've got graph paper. If you don't, you're just going to have to watch me. But using a sheet of paper, graph paper, create a coordinate grid and then plot these 4 points. After you've plotted those and you connect the dots, you'll see that it has formed a quadrilateral. And what your job is to use what we learned in chapter 6 to enlarge the quadrilateral so that the image has a scale factor of 2 compared to the original. So go ahead and do that and pause the video and then come back to us, and I'm going to turn the page and you'll see how I've done this. So here we are. The red quadrilateral is quadrilateral MNPQ with these as the vertices. After applying a scale factor of 2, and if you recall from our dilations, we would have said that each one of these XY coordinates are going to change such that the X coordinates get doubled and the Y coordinates get doubled. So I've taken the 0 times 2 is 0 and 3 times 2 is 6. Plot that point. This is the image of point M. 4 times 2 is 8 and 0 times 2 is 0. So N1 is the image of point N after dilation. Point P, when you multiply the X times 2 and the Y times 2, becomes 4, -4. So here is the image of P. And then point Q, -2, 1, becomes -2, 2, and so on and so forth. So what has happened here? It looks like our sides are double the length because of the scale factor being 2. Now the question is, what has happened with the angles? So if you look at these angles, I can move this guy around. Oh no, I didn't attach. Okay, that's fine if it's not attached to points. I can move this guy around to prove it, but you might need to, on your graph paper, pull out a protractor and actually measure each one of these angles. Like angle Q looks like it measures about 80, maybe 85 degrees, somewhere in there. And then go through and measure angle, the image of Q, and does it end up being the exact same thing? It looks like it does. So you can see, and we did learn this back in chapter 6, get out of there, there you go, that when you dilate a figure, while the side lengths grow or shrink according to your scale factor, the corresponding angles will be exactly the same. So if I move this guy around up to here, over to here, and down to there, it looks like the angles match up perfectly. So this is a key concept for us to understand. What could you say about angle M and the image of angle M? Well, they are congruent to each other. Remember that a conjecture is an inference or a judgment based on incomplete evidence. So based on this work, what conjecture can we make about angles of similar figures? We've talked about this in the past. If two figures are similar, their corresponding angles will be congruent to each other. and then test your conjecture using all the others. Are we noticing the same thing happening? Yep, it always worked. Every one of those angles was congruent. So yes, we've revisited this concept. When you're dealing with similar figures, the corresponding angles of the two similar figures will have the exact same measure. They will be congruent to each other. All right, so imagine the two pairs of corresponding angles in two triangles are equal in measure. What could you then conclude about the third set of angles? All right, so what do we have here? It looks like we've got angle B here and angle E. They're the corresponding angles of these two triangles that are similar to each other. And it appears as if they are exactly the same, and they should be exactly the same because they're similar figures. And angle C and angle F, they are also congruent to each other. So what does that mean for the third set? Do we have any choice? No, we don't. If two of these angles are congruent, then the third one has to be. There's just no way around it. Because remember, triangle sum theorem says that when you add up all three angles, they add up to 180 degrees. If I know angle B and angle E are the same, and I know angle C and angle F are the same, then I know that their sums are going to be the same. And when you take 180 minus those sums, you're always going to get whatever the measure of angle A or angle D are. So that would be a way of proving it if you needed to show the proof, but this is basically what we're saying. If two sets of angles are congruent, then the third set must also be congruent. So we'll make a conjecture, and this conjecture is called angle-angle similarity in triangles. You want to try and create this conjecture on your own? You may not quite understand how conjectures work yet because we've only dealt with them a couple times. I'll just go ahead and show it to you. If you feel like you can come up with a conjecture for when you know that two of the angles are congruent, what do you know about the two triangles? Go ahead and pause it if you want to write it down and then see how yours compares to mine. But I'm going to go ahead and reveal that. This is the conjecture for angle-angle similarity in triangles. If two triangles have two sets of congruent angles, then you know the third pair are congruent, and therefore the triangles must be similar to each other. So if we know that for sure, if we can prove that two of the corresponding angles of two triangles are congruent to each other, then we know the third one will be, and then that takes care of the rule for similarity between two shapes. All the corresponding angles are congruent to each other, therefore they are similar. All right, so the relationship in the previous problem is called angle-angle similarity. Go ahead and read through this. In this figure here, we're trying to determine whether or not triangle ABC is similar to triangle CDE or EBC. It doesn't really matter the order that we put those. So how could we prove it? Well, let's take a look at this. First of all, let's make sure we get these symbols down. This symbol right here means is congruent to. It's the geometry way of saying is equal to. In geometry, they also could be similar to. So if two shapes are similar to each other, but not exactly the same size, then we would use this symbol. There's no corresponding symbol to that in algebra. And I guess maybe, no, not really, there isn't. So this means is congruent to, which is like is equal to, and this means is similar to. So what do we see here? First thing I would do is look at angles ACB and angle ECB. Those are vertical angles. And we know, we've learned that when two lines intersect each other, the angles that are vertical to each other are always the same exact measure. Where did you go? I missed you. Okay, back to this. Okay, and then we only have to prove one other angle, one other set of angles. We could have, I could have chosen angle B and angle CDE, but I chose to go with angles A and E, mainly because it's so much easier to just write angles A and E. And we know that line AB is parallel to line DE, Because these are right angles, which means that this line is perpendicular to both of them. So if this line, this transversal is perpendicular to both line AB and DE, then AB and DE have to be parallel to each other. So I could have just chosen angles B and CDE as our alternate interior angles, but I chose these. And so that's a transversal line AE intersecting line AB and DE, which are parallel to each other. Therefore, they are alternate interior angles and therefore are congruent. So simply by looking at those two, we can determine that triangle ABC is similar to triangle EDC because of angle-angle similarity. All right, Eleanor and John were working on a geometry problem together. They knew that in the figure below, line M is parallel to line BC. So you see line M located here, and BC, they've got those two arrows there signifying that they are indeed parallel to each other. They wanted to find the side lengths of each triangle. First, they decided that they needed to show that these two triangles are similar to each other. So the triangles that they're talking about, this is triangle AED, and this is triangle ABC. So are those two triangles similar to each other? If they are, then we know something else. We know that corresponding sides will be proportional to each other. That was something else that we learned in chapter 6. And they would be proportional based on a particular scale factor. How much bigger is this one than that one? We don't need to find that out. We could find it out, but that's not what this lesson is about. So all we're going to do is prove that triangle AED is in fact similar to triangle ABC. So how can we do that? Well, directions say use the diagram at the right to name the pairs of angles, equal angles that Eleanor sees, and then why they're equal. Well, I'm going to use something that's called a two-column proof. And the two-column proof looks like this. On the left, we're going to stake our claim, or make our claim. We're not staking claims here. We're making our claim, and then we're going to prove it to be true. And so, for instance, what's the first thing I want to prove? I want to prove that angle EAD, which is this angle right there, is actually congruent to angle BAC, which is also this angle. Well, they're the same angle, so they have to be congruent to each other. So that one was pretty straightforward. Now let's look at angle AED. This one right here, and angle B, which is right here. How do those two angles compare to each other? Well, once again, if line M is parallel to line BC, then this line AB is a transversal, and the line, or angle 1 here, is going to be, I guess I should have just called it angle 1, huh? Oh well, whatever. Angle 1 corresponds to angle B, so they are, in fact, corresponding angles and are proven to be congruent to each other. That's all we need to prove it. We've got two sets of angles of these triangles that are congruent, which means the third set has to be congruent. So by way of angle-angle similarity, they are, in fact, congruent to each other. But we'll prove it just to prove it. Angle ADE, which they're calling angle 2 here, which I didn't write there, but I could have, and angle C are in the same kind of situation as angle 1 and angle B. They are corresponding angles with this transversal line AC intersecting line M and line BC. So for the same reason, they are congruent to each other. They're corresponding angles. So we've proven that all three of the sets of corresponding angles are in fact congruent to each other, which means that the two triangles are similar. So with that being the case, now we can pull up some proportional reasoning to solve for these side lengths. So taking these two, remember this is the one that's lifted off the top, and this is the combination of the top triangle and the overall triangle, this bottom trapezoid. And so notice this proportion says side 3 corresponds to this side right here, which is 3 plus 5. And side x here corresponds to this side, which is the x plus the 8. So what we need to do is we need to solve that proportion. So go ahead and pause the video. This is going to be the last problem that we do. Pause the video and see if you can solve for x here. When you come back, I'll work through the problem with you. All right, hopefully you got your answer and your answer matches mine. First thing I'm going to do is simplify this fraction. So instead of 3 over 3 plus 5, let's call it 3 over 8. And then x over x plus 8. This does not look like a lot of fun for a giant 1 problem, so I'm just going to go straight to cross multiplying. So when you cross multiply, you get 8 times x, and you get 3x plus 24 because you have to use distributive property there. And then by combining like terms, we end up with 5x is equal to 24 after subtracting 3x's from each side. And then the last step we would do is divide each side by 5. So what is 24 divided by 5? That's going to be the length of x. And so if you got an answer of x is equal to 4 4/5 or 4.8, then you did everything correctly. So remember, there were a lot of things that we had to prove here. Before we could even use this proportional reasoning, we had to prove that these two triangles were in fact similar to each other. It didn't state anywhere that they were similar. But we know now something about angle-angle similarity, and we know what happens when you dilate figures. The similar figures that are created from the dilation end up having the same measures for all of their corresponding angles. So with that in place, and with the proportional side lengths, we're able to solve for missing sides. Okay, so feel free to back this video up, watch it over again, watch it as many times as you need to fully understand what we're talking about here. Please draw the diagrams from your homework into your journal and show all of the processes. Geometry is a very visual mathematics. I cannot stress enough how important it is for you to draw those pictures and label everything. So do all of your work. Good luck in your homework, and we'll go over the problems in our homework tomorrow. All right, take care.
Hey, feeling good, like I should. When in dark, walk around the neighborhood.